In the last section, we have discussed the definition of compensation and various techniques of the compensation or various schemes, how the power flow can be controlled either by manually or by automatically by the help of power electronic switch. Now in this class or in this section of discussion, we shall discuss the types of the compensation and their working principle. So there are fundamentally or primarily 4 types of compensation. We have primarily we have series compensation, then we have a shunt compensation, then we have a series compensation, and we have a series shunt compensation. Now this is a typical example of series compensation. Series compensation. This is a typical example of shunt compensation. And this is a typical example of series shunt compensation. This typically calls TCSC. I'll discuss later on. Thyristor control series capacitor. Thyristor control series capacitor. This shunt compensation is called TCR, thyristor control reactor, and this is called UPFC, unified power flow controller. Unified power flow controller. So TCSC stands for TCSC stands for thyristor controlled series capacitor. What is TCR? TCR stands for thyristor controlled reactor. And lastly, we have shown another shunt series compensation, that is called UPFC. It is called unified power flow controller. Now let us quickly compare these two. What is series compensation and what is shunt compensation basically? Series compensation, as I already told you, that you must connect a capacitor in series with that line. It will change your reactance and automatically you will get the enhanced power or decreased power depending on the value. And now with that, what does shunt controller do or shunt compensation do? Suppose this is the line, we have a reactor or maybe a capacitor in parallel with that line. So either that inductor is absorbing reactive power or it delivers reactive power or this capacitor delivers reactive power. By doing this, it can control the voltage at any bus or voltage at the subsequent bus. This is the purpose of shunt compensation. As a series and shunt compensation, if you mix them, it will both do both. Now if you compare, what does it do? That series compensation, it injects a voltage in series with the line. It injects because a current is flowing, it is providing a reactance. This capacitor is providing a reactance, okay? So current multiplied by reactance, it will give you a voltage. So that voltage is added with the series with that line. So it is a voltage injection process. Series compensation is a voltage injection process. This is number one. On the other hand, the shunt controller or shunt compensation, it injects or draws current from the line. It injects or draws current from the line. So it's not about voltage. It current. It injects current in the line or draw. In case of an inductor, it is drawing current. In case of a capacitor, it injects current. Okay. So this is the primary difference between series compensation and shunt compensation. Its voltage has been injected in series with the line for series compensation, and for shunt compensation is the current has been injected or drawn the line or from the line. Now for the series compensation, it is primarily used to control the flow of active power. It is primarily used to control the flow of active power. As you have seen, it is directly proportional to 1 by x. So if you change x, then P will change automatically. And now what is happened in case of a shunt compensation, it is primarily used to control the voltage at different buses. So basically this reactive element L or C, it injects or draws the reactive power. So reactive power helps to maintain the voltage at any bus. That is why it is said, or it is used, or shunt compensation is primarily used to keep or to control voltage at different buses. Now why? Now the third statement I have written is P is closely coupled with angle. That means P is a very close companion of alpha, or not alpha, rather it is delta, and Q is a very close companion of V. This statement that voltage is closely coupled to reactive power Q and P is closely coupled to the phase angle delta. Now why I have written this, it can be proved mathematically, but for the time being you consider this statement. The proof of this statement is beyond of the scope of this section, so I am skipping that. So due to this fact, for series compensation is primarily used to control the flow of power, active power rather, and since it is drawn reactive power or injects reactive power, the voltage is maintained by shunt compensation. This is the difference. Now let us first consider the first case of a series compensation, which is called TCSC. This is an example of series compensation. Now this is the series capacitor connected in series with the line. Okay, this yellow shaded capacitor, it is the capacitance connected in series with the line. So this is C and this is the line. It is connected series in series. So these are, if they are the two terminals, they are in. Now the rest, whatever you are seeing. Now the rest, whatever you are seeing, this portion, an inductor, then an anti-parallel thyristor. This is the controlling circuit. This is the controlling circuit. We have an inductor L, which provides or which offers a reactance of X, and we have a thyristor switch S1 and we have a S2. Now whatever this reactance or inductance will provide, it will be not providing XL, but this is purely dependent on this thyristor. So basically, what is net reactance of TCSC is, of course, we have XC, but we have a parallel reactance XL, but that parallel reactance again it's dependent on these two thyristor. Now, so its value of XL will be depending on the firing angle or delay angle. So XL will be function of alpha. So this will be the net reactance. So since this total reactance will be the net reactance of TCSC and it is again dependent on alpha, so the net reactance of TCSC will be dependent on alpha. So this expression tells that the net reactance of TCSC is dependent on alpha and it is a tunable parallel LC circuit. Basically it is tunable parallel LC circuit. So you can, now what is XL alpha? Formula is there. XL alpha is given by this formula. I'll give you 3 to 4 problem or 3 to 4 data. Now if you fire alpha at 0 degree, if you fire alpha at 0 degree, your XL alpha becomes only XL, because this sin alpha, sin 0, 0, this is 0, so pi by pi it is 1, so XL alpha becomes XL. Now if you increase the value, if you take x equal to 30 degree, then XL alpha, it will become 1.48 XL. So its value is increasing. If you further increase, alpha is equal to 60 degree, then your XL alpha will be increased by a far more amount, which is equal to 17.34 XL. So it keeps on increasing. Now if you do like that, one point will come at some angle that XL will be a very large value. We say that one as an infinity. Now if you further increase your alpha, then this XL alpha will become a negative value. And if you till further increases up to 90 degree, then XL alpha will become at 90 degree, it will become minus 3.14. So basically it will take this shape. It will take this shape. So if you in your x-axis it is alpha and your y-axis it is XL, so it will roughly takes this shape. Okay, and suddenly it falls and it takes this. So this region is the inductive region. Inductive region, and this region is capacitive region. And this alpha at which XL alpha becomes XC, it's called resonance. Resonance frequency or resonance, resonance angle, for which XL alpha becomes, you see XC has a same value, XC has a same value, XC has a same value, right? But XL now still keeps increasing. So at some point of time it will come when this XL and XC becomes equal and opposite. So this is called the resonance. So basically by controlling this alpha, we are providing a variable we are offering the variable XL value that indeed creating a variable reactance in TCSC. So this is how TCSC works. So basically it is a tunable parallel LC circuit which offers variable reactance in series with the line, and this totally depends on the angle of this alpha. That means the firing angle of this two back-to-back connected SCRs. This is the working principle of TCSC, that means thyristor controlled series capacitor. Now let us say we have a shunt compensation. How it works? Let us consider this diagram. So this is basically exactly the same diagram which I have shown you previously. It is TCR. So again you see one reactor is providing some reactance XL and it is controlled by two back-to-back connected SCRs. So whatever reactance it will provide, so basically that will be a function of alpha. Right, that will be a function of alpha depending on at which angle SCR is being fired. So this will be nothing but XL alpha. Let us say we have a fixed value of capacitor which injects some reactive power, and this is the harmonic filter. Now let us say, for the time being, let us say voltage at this bus, let us say this bus is A, this bus is B, and in between we have a transformer. Let us say voltage at bus B is reduces. Voltage at bus B reduces. So how it can be made to its nominal value or to its rated value? So how, the question comes, how VB or deep in voltage magnitude can be brought to nominal value. That is the question. The answer is we must inject reactive power. We must inject reactive power. Who will do that? Only capacitor, because capacitor only injects reactive power into the system. But this has a problem. If that capacitor injects some reactive power, well and good, but that reactive power injected by the capacitor, it will go to the bus, and let us say that voltage, which is, I am giving you a rough example, the voltage was, let us say, 0.93 V. Now we are supposed to take this 0.93 V to only V, but instead of having that, by inclusion with that capacitor, this 0.93 V becomes, let us say, 1.07 V. That means this capacitor, because that is the problem of this fixed capacitor, because this Q it cannot be controlled. Whatever it will inject, it will be a same value, unique value. So by 0.93b, instead of making 0.93b to b, it makes 1.07b. Understand? So again, that will be a problem. So it will be a case of over voltage now. We were experiencing a case of under voltage. Now on the, if we this switch is on, then some reactive power is injected into the system. By that injection of the reactive power, it is so large that now voltage becomes excess over its nominal value, and it becomes 1.07. That means 7% more than its nominal value. Initially it was 7% less than its nominal value, now it becomes 7%. So it is 14% shift. Now again, how this 7% excess can be made, brought to the nominal value? The answer is this. Now you calculate what amount of reactive power that needs to be absorbed by this reactant, and and signal is sent to that gate circuit of those SCRs, and that SCR will be fired accordingly at the appropriate angle of alpha. Then that appropriate angle of alpha will induce some fraction of XL, let us say 0.55 XL. It will induce, or it will inject a value of 0.55 XL. So this 7% excess voltage. So that much amount reactive power will be absorbed only. So this is the function of TCR, that is the function of shunt compensation. So in this way, capacitance can inject a fixed amount of reactive power, that is very good, but that does not guarantee that my voltage will become at nominal value. It can go below nominal value, it can have above nominal value. So how, if it is above a nominal value, then how can it be again brought to the nominal value? By using this TCR. So TCR, by controlling this thyristors, it will offer some fraction of XL, okay, just like the TCSC fraction of XL. So it will offer a fraction of XL, only 50% or 70% or 40%, whatever it may be, and accordingly the reactive power from the system will be absorbed. That is the solution. Now one example or one application of this TCR to minimize Ferranti effect. To minimize Ferranti effect. What is Ferranti effect? Your VR becomes greater than Vs. How to make VR? It is not desired, na? It is not desired. Receiving end voltage is taking upper hand over sending end voltage. It is not desired. It is not desired. It is not desired. Not desired. So if it is not desired, then how to make VR is equal to Vs? How to make VR is equal to Vs? How to make it? So answer is the application of this TCR. So whatever, why this is greater? Because reactive power due to the charging current, Q is, that means the injecting Q is more or leading Q is more, Now you need to absorb excess amount of Q, so that make it down to equal to Vs. So that is the role of TCR. So if you now adopt, or if you fire your SCRs at an appropriate angle, though the excess amount of Q will be absorbed by this inductor, and it will be make VR is equal to Vs. So this is the application of TCR. We can use it in the to reduce or to minimize or to nullify the Ferranti effect. This is one application of series compensation and one application of shunt compensation each. Now I am not going to details in UPFC, that is Unified Power Flow Controller. One point I have to mention here is that for series compensation, and for shunt compensation, it is primarily control P and it is primarily controlling Q. Series and shunt compensation, we can control both P and Q. That is the advantage of series and shunt control. That is exactly done in UPFC. If you see this diagram, this is a shunt controller which is called STATCOM, synchronous static compensator, STATCOM, and this is a series compensation. You see, this injects a voltage in series. You see, this is connected in series with the line, and this is the common DC link, that is this capacitor. So this is the diagram of UPFC. So this STATCOM and SSSC can share active and reactive power among them both without any dependency on the line side. It can inject power, it can draw power, both active and reactive from the line, right, as well as this series compensation or series compensator. This is the UPFC. So if you adopt UPFC, you can control P and Q both without the dependency on the line side parameters. Now lastly, what are the advantages of compensation? It is increase or decrease the flow of power, okay, as per our requirement. It either increases or decreases the flow of power, reduce the loadability of the line. It has already been explained in the first slide, that is how by inclusion of one single capacitor, how that 80 megawatt or 100 megawatt can be reduced to 70 megawatt. Automatic voltage regulation can be achieved by the using of those SCRs, IGBTs, that is the power electronic switches. And lastly, increases the stability of the system, of course. Why? Because if you follow this curve and this is the curve, what are the difference? This is the without C and this one is with C. So with C, our transmission line can enhance or can transmit more amount of power that indeed will increase its stability limit, because I have already told you this is the stability limit, steady state stability limit. So that stability limit increases. So it is very easy to control the power system. So this is all for this compensation topic. So just briefly we have discussed what is compensation, how what is the role of compensation, why compensation is needed, what are the types of the compensation, and working principle of different compensation. Just a brief introduction of the compensation has been discussed because this compensation is an advanced topic and it is typically designed for PG course. But since this Power System 1 course is for UG course, so a brief introduction has been discussed with you. So with this, I am ending this session as well as this topic. From next session, we shall start a new topic. Thank you.